Hello, welcome to my channel. Today we are going to discuss about single phase full bridge inverter, how it works, its circuit, waveform, as well as the simulation on MATLAB Simulink. So let's start the video without further ado. Single phase full bridge inverter is a circuit that converts DC power into AC power. It utilizes four switching elements arranged in a bridge architecture to produce alternating output voltage. The switching elements are usually semiconductor devices, either MOSFET, BJT, IGBT, or power diodes. In this circuit, we are using MOSFET. There will be two switches in each branch, and it operates by alternatingly turning on and off switches in complementary sequence. So for example, MOSFET 1 and 2 will be switched on, or MOSFET 3 and 4 will be switched on. All the four switches won't be turned on at the same time. This allows current to flow through the load. In this circuit, the load is a resistive load, and you can see on the circuit there is a positive on the right hand side and negative on the left hand side. This is the conventional reference used. It will be either given in the question or you can determine on your own. Now let's look at the operating principle of the circuit with the help of waveforms. Initially, MOSFET 1 and 2 will be switched on, usually with a pulse generator. When 1 and 2 is switched on, MOSFET 1 and 2 is shorted. This allows current to flow in this direction. Now, the current direction is opposite to the conventional reference, as I mentioned before. That's why the voltage drop across the resistive load won't be V0, but rather minus V0, as you can see in the waveform. The first waveform is the source voltage, which is DC, so it's a constant voltage. The second waveform is MOSFET 1 and 2. So as you can see, initially MOSFET 1 and 2 is in on state and MOSFET 3 and 4 is in off state, and you get a voltage drop of minus V0. Now before turning on MOSFET 3 and 4, we intentionally add a small amount of delay. This is known as dead time. As you can see, there is a small gap. There is a small gap in the waveform. This delay is very important. This is called dead time. This is to prevent all the four MOSFETs to switch on at the same time. This will cause the conduction time to overlap. When the conduction time overlaps, there will be short circuit in the circuit and no current will flow through the load, and the load won't function properly. So we need to add a small amount of delay. After adding a delay, we switch on MOSFET 3 and 4. MOSFET 3 and 4 will be shorted and the current will flow in this direction along the conventional reference. That means the voltage drop will be V0. As you can see in the waveform, this repeats continuously to form an alternating voltage. So that is it for the conversion of DC to AC. There is a small advantage and disadvantage. The advantage is that what you give in the input, you are getting it in the output. So Vs is equals to V0. We are talking about ideally, theoretically. Practically it might be less, but not as in Vs by 2 like in half bridge inverter. And the disadvantage is that the output we are getting is a square wave, which is a formation of many small frequency components, and the load we are adding is a single frequency load, so it might not function properly. Hello. To create a single phase full bridge inverter on Simulink, at first we open Simulink on MATLAB and go to libraries. After we go to libraries, we collect our necessary components and add on our blank module. So let's start with collecting the components. At first we go to sinks and add scope to our new model to check voltage measurements and get a voltage graph. Then we go to source to get our pulse generator for all the four switches. Then we type in MOSFET for our semiconductor switch. Then we search voltage and get a DC voltage source, because we are converting from DC to AC, and a voltmeter. To get a resistive load, we search series RLC, the first component. The series RLC component will have all the three, but we will modify it and get only resistance, because it's a resistive load. And the most important component is it is used for modeling power electronic systems and make sure the circuit performs complex nonlinear behavior and deal with high frequency and high power level systems. Then we open our blank model and arrange the circuit. Adding component once is enough. We can copy paste components to create multiple copies. After completing the circuit arrangement, we will start our simulation. At first, we need to input our specific requirements. For example, I will set the resistance value to 103 ohms, the DC value to be 103 volts, and the frequency is, I consider the frequency to be 50 hertz. That means 1 by 50 is 0.02 seconds, which is the time period. So 0.02, and the pulse width will be 50%. Why 50%? Because in inverter design, maintaining a pulse width of 50% is often preferred due to its symmetrical waveform characteristics. The balanced duty cycle ensures equal on and off states within a defined period. That is the reason why we set pulse width 50%. So 50% on, 50% off. For the next pulse generator, we will provide the same values with 0.02 period, pulse width of 50, but a phase delay of 1 by 100. That means after 1 by 100th second, we will get our high level. That means after 1 by 100 we will get 1, but for the first pulse generator we will get 1 at 0. So 1 by 100 is 0.01. And if we start, so the first waveform is the output voltage. The second waveform is the MOSFET. Let's see, is for MOSFET 1 and 2. So the second waveform is for MOSFET 1 and 2, and the third waveform is MOSFET 3 and 4. When MOSFET 1 and 2 is on, MOSFET 3 and 4 is off, and we get -100 according to our theoretical waveform. The same concept, because we set the conventional reference as positive on the right hand side, negative on the left hand side, and the graph is the same. This is for 50% pulse width, but remember, according to the theoretical explanation, we need to provide a delay, which is the dead time. We set the dead time by adjusting the pulse width. For example, instead of considering 50% as the pulse width, we set for a 5% for a 5% dead time, we set pulse width to 45. 50 minus the dead time percentage. So for a 5% dead time, we set 45. Apply 45. This is for 5% dead time. And we can see a dead time is introduced. There is a small brief period of time where the output voltage is 0. This is called the dead time, and this is the actual waveform we need. This is the actual output voltage we need. Now remember the exception where if we increase the pulse width to more than 50%, what happens? Let's see if we set 75%. This is more than the 50% pulse width. Our output is decreased. This is because the conduction period is getting overlapped between the switches. That means there is a period of time where all the 4 switches are getting turned on and there is no current flowing through the load. This is a short circuit in the circuit. And that is it for the simulation. This is our circuit. We set the time period to 0.02 because 50 Hz frequency, 45% pulse width for both, phase delay of 0.01, and 103 ohms of resistance, 103 volts of DC supply. And that's it. Thank you.